All right, so for elements, the molar mass is the mass of 1 mole of atoms of that element. For compounds, the molar mass is the mass of 1 mole of molecules or formula units of that element. So when you guys are using Avogadro's number for compounds, you will say 1 mole of that compound equals 6.02 times 10 to the 23 molecules. Or you could say 1 mole of that compound equals 6.02 times 10 to the 23rd formula units of that compound. So we're going to do some examples like that. So in this problem here, what is the mass of 4.78 times 10 to the 24 NO2 molecules? So we're given this problem in molecules. Well, what relates molecules to moles? Avogadro's number. Okay, so we know that we can get from molecules to moles using Avogadro's number, and then the question is asking us for the mass. How do we get from moles to grams? We use the molar mass. All right, so let's sort it out. This is what we're given. This is what we need to find. We're going to start with what we're given, our molecules. We're going to use Avogadro's number, all right, to get out of molecules and into moles. And then we can use the molar mass of NO2 to get out of moles of NO2 and into grams of NO2. Let's see how this works out. All right, we just calculated the molar mass of NO2, so we already found that, and we do know Avogadro's number. Okay, a little bit of time here. All right, so starting with what we were given, 4.78 times 10 to the 24 NO2 molecules. We're going to use Avogadro's number, 6.022 times 10 to the 23rd NO2 molecules, and convert that into moles. Okay, so our molecules cancel. This was an awfully long problem, so it ended up having to go on the next line. So now that we're in moles of NO2, we can use the molar mass of NO2 to get into grams. All right. So we're going to take our 4.78 times 10 to the 24, divide by 6.022 times 10 to the 23, and then multiply by 46.01, and to the correct amount of significant figures, which is 3, our measured value, our answer pops out as 365 grams of NO2. All right, let's check the answer. Yes, the units are correct. And does the answer make sense? Because the number of NO2 molecules is more than 1 mole, the answer should be more than 1 molar mass, so more than 46.01 grams, which it is. Therefore, the magnitude of the answer is reasonable. Nice. All right, let's try this one. How many H2O molecules are in a sample of water with a mass of 3.64 grams? All right, so this time we're starting in grams and it asks us to get to molecules. Well, how can I get from grams to molecules? I know I can get from grams to moles using molar mass, right? Okay, then once I am in moles, then I can use Avogadro's number to get from moles to molecules. So let's see this sorted out here. Let's try it. So starting with what we're given, 3.64 grams, okay, and this is of water. And we need to use the molar mass of water to get into moles of water. All right, the molar mass of water is, we have there we go, try that again. 1 mole of H2O is 18.02 grams. And all I did was look up the molar mass of 2 hydrogens plus the molar mass of 1 oxygen and add them together. All right. So our grams cancel, and now I'm in moles of water, but I don't want to be in moles of water. The question asks me to get into molecules of water. So how can I get from moles to molecules? Avogadro's number, okay? So I know that 1 mole of water is 6.022 times 10 to the 23rd molecules, all right, of water. And now we just have to calculate that out. So in multiplying 3.64 divided by 18.02 multiplied by 6.022 times 10 to the 23, what's going to pop out on your calculator with the correct rounding and significant figures is 1.22 molecules of water. I'm going to show all of our units have canceled here. All right, so here are some more practice problems that you guys can try. Okay, so now we're going to use chemical formulas as conversion factors. So let's just use something simple to start with. All right, we can see that this clover has 3 leaves, all right? So we can use that as a conversion factor. 1 clover has 3 leaves. So if I have 14 clovers, how many leaves would I have? Well, we have 14 clovers. We're going to use our 3 leaves per clover as our conversion factor. Our clovers cancel, and we would take 14 multiplied by 3, and we'd end up with 42 leaves. All right, similarly, now with carbon dioxide, the formula for carbon dioxide is CO2. This means that there are 2 oxygen atoms per 1 CO2 molecule. So you can write this as 2 oxygen atoms in 1 CO2 molecule. Similarly, if you had 2 dozen oxygen atoms, you would have 2 dozen oxygen atoms in 1 dozen CO2 molecules, all right? And you could also write there are 2 moles of oxygen, because there are 2, in 1 mole of CO2, okay? Other conversion factors that might make sense to you. 1 spider has 8 legs, 1 chair has 4 legs, and now if you look here at a water molecule, 1 H2O molecule has 2 hydrogen atoms, or you could say 1 H2O molecule has 1 oxygen atom. All right, so we're going to try to use this in chemical formulas. Determine the number of moles of oxygen in 1.7 moles of calcium carbonate. All right, so let's see here. Okay, let's sort by what we are given. We're given 1.7 moles of calcium carbonate, and we have to find moles of oxygen. So we're always going to start with what we're given. So we're going to start with that 1.7 moles of CaCO3. All right, so this is going to be our conversion factor. So in 1 mole of calcium carbonate, how many moles of oxygen are there? Well, there's 3. Okay, so you can write that as a conversion factor. There are 3 moles of oxygen in 1 mole of calcium carbonate. All right, so this is your relationship that you guys are going to use, and let's see how it's done. So we're starting with our 1.7 moles of calcium carbonate, and we want to get into moles of oxygen, determine how many moles of oxygen there are. So we have that conversion factor, knowing that there are 3 moles of oxygen and 1 mole of calcium carbonate. Our moles of calcium carbonate cancel, and we end up with 5.1 moles of oxygen. All right, are the units correct, and does it make sense? The units of moles of oxygen are correct, and the magnitude is reasonable, as the number of moles of oxygen should be larger than the number of moles of calcium carbonate, because for each calcium carbonate atom, you have 3 oxygen atoms. All right, let's try this one. Determine the number of moles of oxygen in 1.4 moles of sulfuric acid. All right, so we're always going to start with what we're given. So that's 1.4 moles of sulfuric acid. How many moles of oxygen are in that? Well, there's 4. Okay, you can see right here. So we want our H2SO4 on the bottom. So 1 mole of H2SO4, that's our sulfuric acid, contains 4 moles of oxygen. All right, so now let's calculate that out. We're going to take our 1.4 times 4 and see what we get. All right, when I put that in my calculator, my moles cancel, my moles of sulfuric acid cancel, and I end up with 5.6 moles of oxygen. What if the problem had asked for grams of oxygen? Could you do that? Easily, right? You guys could just use the molar mass to get out of moles of oxygen and into grams of oxygen. All right, good job. All right, we're going to talk about one very similar to what I was just describing on the previous slide. Convert between grams of a compound and grams of a constituent element. Find the mass of sodium in 15 grams of NaCl. Well, this is actually really easy. We've learned all of the tools. So we always start with what we're given, 15 grams of NaCl. Can't I get out of grams of NaCl and into moles of NaCl using the molar mass? How do you always get from grams to moles and moles to grams? The molar mass. All right, so they've already calculated the molar mass of NaCl for us. All right, so it's 58.44. So we're going to start here with our 15 grams of NaCl, and we're going to use the molar mass there to get out of grams of NaCl and get into moles of NaCl. Well, now that I'm into moles of NaCl, can't I use that ratio that we were talking about? There is 1 mole of sodium in 1 mole of NaCl. You can tell that because there's 1 sodium and there's 1 chlorine. All right, so now that we're into moles of NaCl, we can use this ratio. 1 mole of NaCl has 1 mole of sodium in it. All right, so now not only does our grams cancel and we got into moles of NaCl, but now our moles of NaCl cancel and we're into moles of sodium. All right, now, just like what I was saying on the last problem, couldn't you get out of moles of sodium and into grams of sodium? Very easily. Always to get from moles to grams and grams to moles is using the molar mass. The molar mass of sodium is just on the periodic table, okay, and they have it listed for you here. All right, so I'm going to put my moles on the bottom and my grams on the top because I want my moles to cancel, and I'm going to calculate this out. 15 grams divided by 58.44. You don't really need to do anything here because it's 1 to 1. And then multiplied by 22.99, and what pops out in your calculator is 5.9 grams of sodium. Awesome job. So what we just learned is that the mole relationship from a chemical formula can be used in many calculations. The relationships inherent in a chemical formula allow us to convert between moles of a compound and moles of its constituent elements. Okay, so we can see here that 1 mole of CCl4 has 4 moles of chlorine. So you could use that as a conversion factor. And you also know that 1 mole of CCl4 has 1 mole of carbon, which could also be used as a conversion factor like we just did. All right, good job. That wraps up this video.